Hi, Assalamu alaikum everyone. Now it's time to look at the final lesson before we go to organic chemistry. Lesson 55, Factors Affecting the Reaction Rate. Today we need to explain factors affecting reaction rate consist of pressure, concentration, temperature, catalyst, and particle size. We also need to explain the effect of temperature on the reaction rate using Maxwell-Boltzmann distribution curve. What are they? Then we need to explain the effect of catalyst on activation energy based on energy profile diagrams of exothermic and endothermic reactions. Then we're going to relate rate constant and activation energy with temperature using Arrhenius equation. Here we are going to determine K, activation energy, temperature, and A using Arrhenius equation by calculation and graphical method. There are 5 factors that will affect the rate of chemical reaction. Number 1 is concentration. Number 2, pressure. And then temperature. This is regarding Arrhenius equation. And then catalyst. And finally, particle size. This is the summary for the things that we are going to learn today. The first one is concentration of reactants. If it increases, the reaction rates will generally increase. And for pressure, if the pressure increases, the volume will decrease, making the molecules of the gas near to each other. So the number of collision increase, making the reaction rate increase. The temperature will generally makes reaction rate increase as it increases. And then catalyst will speed up the reaction. And finally, particle size. The rate of reaction will increase as the size of the particle became smaller. Let's look at the concentration. The change in concentration of reactants will change the number of particles per unit volume, and this will increase the number of collisions per unit time in that volume. If concentration is doubled, the number of collisions would also double, because in any given volume there would be twice as many molecules that could collide. Consequently, the rate would increase by a factor of 2. According to the collision theory, an increase in the number of collisions will bring an increase in the rate of reaction. Number of molecular collision is then, we can say, proportional to the concentration. Now let's look at the second one, pressure. When pressure is applied, the volume will decrease. The number of molecules per unit volume increases, resulting in more collisions per second. This is kinetic theory, if you remember chapter 2 in Sem 1. The number of effective collision increases, so the rate of reaction also increases. Look at this figure. You can see at low pressure, the molecules are far away from each other. At high pressure, the molecules are near to each other, so the number of collision will increase, hence the rate of reaction will increase. Here is another figure showing that for a low pressure, the reaction rate is in green, so it is having the lowest curve. And then for moderate pressure, the blue one is here. If it is high pressure, the rate of reaction will increase as shown in this figure. The most important part in this subtopic is how temperature affecting the rate of reaction. The higher the temperature, the higher the rate of reaction would be. But how? This can be explained in terms of kinetic theory. This is shown to you, figure 3.20. A Maxwell-Boltzmann distribution curve. We can see here the fraction of molecule having a certain kinetic energy is plotted against the kinetic energy. And at temperature 1 in blue, the number of molecules that have enough kinetic energy to react is here, very low here. And then for temperature T2, this is a higher energy. In red, you can see the curve is slightly lower, but it is having a higher energy compared to T1. You can see here, EA is situated here on the right side of the graph, and then T2 has higher value than T1 at EA, whereby molecules with enough kinetic energy under the curve is more for T2 compared to T1. What is Maxwell-Boltzmann distribution curve? It defines the distribution of the different kinetic energies of particles in a system. From the figure that we have seen previously, T2 is a higher temperature. The area under each distribution curve is proportional to the total number of molecules. There is wide range of molecular energy. A few molecules have low energy, a few have high energy, but most have values somewhere in the middle. So we call this as average kinetic energy. Okay, let's read more about the curve. The shape of the graph changes with temperature. The curve flattens at the higher temperature. At higher temperature, the fraction of molecules with energy greater than the activation energy increases. This is the main reason for the increase in rate of reaction. The shaded areas, blue and red, represent the number of molecules traveling at a speed equal to or greater than EA. For T1, only a small fraction of molecules have EA to react. But for T2, the fraction of molecules having enough EA is greater. The number of efficient collision is increased. The rate of reaction also increases. Ultimately, we can say the higher the temperature, the greater the number of molecules moving at high speed. So only fast-moving molecules have sufficient kinetic energy to overcome the activation energy. It was established that a rate of reaction doubles for every 10 degrees Celsius rise in temperature. Number 4, catalyst. Let's read about catalyst. A catalyst is a substance that increases the rate of chemical reaction without itself being consumed. For example, the enzyme in our body. It increases the rate of a chemical reaction by providing an alternative reaction pathway with a lower activation energy, so that more molecules attain the minimum kinetic energy needed for the reaction. Catalyst does not affect the enthalpy of reactants or products. Figure 3.21 shows the comparison of the activation energy of the catalyzed and uncatalyzed reaction. As you can see, the blue curve here is the reaction that is using a catalyst, but the red one is having a higher activation energy because it does not have a catalyst. This is a very clear graph to show that catalysts will increase the rate of reaction by providing an alternative pathway and decreasing the activation energy. Here is the energy profile diagram for an exothermic reaction, where you can see the yellow line is for the catalyzed reaction, where the activation energy is lowered compared to the red line, which is non-catalyzed. For endothermic reaction also, we can see the yellow catalyzed line is having a lower activation energy compared to the red non-catalyzed reaction. Here is another Maxwell-Boltzmann distribution curve where the number of molecules is plotted against kinetic energy. So the area under the curve would be the amount of molecules that have enough kinetic energy or activation energy to react. So without catalyst, the line is here, meaning only this much of a molecule is having EA. But for the reaction that is using catalyst, the line is here. So all these purple and blue lines are all is the amount of molecules that have enough kinetic energy to react. When activation energy increases, constant K increases and the reaction rate increases. So when we have a catalyzed reaction, you can see on the right graph here, the activation energy is lowered compared to the uncatalyzed reaction where the activation energy is high here. This is for exothermic reaction. So the rate of catalyzed reaction is higher than the rate of uncatalyzed reaction. Addition of catalyst also increases the rate reaction by increasing the frequency of effective collision, because the catalyst also acts as a surface that can increase the collision. This is by decreasing the activation energy and having a correct orientation. So you can see here, NO is bumped to the metal surface together with CO, and then N and O will be fixed at the metal surface, and then CO will take the O to become CO2. So the metal surface is actually providing a place where the effective collision can occur effectively. Addition of a catalyst changes the value of K, which is the great constant. So we can see here, the rate law reaction rate equals to Ka to the power of X, concentration of B to the power of Y, where A and B is the reactants and X and Y is the rate order. You can see the K there, it will increase or changes. The catalyst reacts by reducing the EA and increasing the A, thus increasing the K. Here shown to you is a formula. This formula is called Arrhenius equation. The dependence of the rate constant of a reaction on temperature can be expressed by the following equation known as Arrhenius equation. As you can see here, the primary Arrhenius equation is K equals to A, the frequency factor, exponential to negative EA, activation energy, over R, gas constant or energy constant, and T is the absolute temperature. We need to add 273.15 for calculation using Arrhenius equation. This equation can also be expressed in a more useful form by taking the natural logarithm of both sides. So we put natural log K and natural log A minus EA over RT. So at two different temperatures where A is constant, Arrhenius equation can be written as natural log K1 over K2 equals to AA over R, 1 over T2 minus 1 over T1, whereby R is the energy constant, 8.314 joule per mole per Kelvin, and the temperature must be an absolute 1. This equation can take the form of a linear equation, a straight line graph. So if you can see here, natural log K is representing the y, and then the slope m is actually a negative EA over R, and then x is the 1 over t, plus y-intercept is the natural log A. So a plot of natural log K versus 1 over T gives a straight line whose slope m is equal to negative E, A, activation energy, over R. And the y-intercept would be ln A, or natural log A. The question on straight line graph is provided in the tutorial part of the chapter, and the empty graph paper also is provided at the end of the question. So go there and try finding the activation energy as a slope. But for now, we're going to do example 3.10 in your textbook. Consider the reaction 2B becomes C plus 3D. In an experiment, it was found that at 300 K, the rate constant is 0.134 liter per molar per second. A second experiment showed that at 450 K, the rate constant was 0.569 liter per mole per second, meaning that the temperatures are already in absolute temperature. It is giving T1 and K1, T2 and K2. So we need to determine the activation energy for the reaction. So the first thing that we need to do is write the formula of Arrhenius that we are going to use, which is natural log K1 over K2 equals to EA over R multiplied by 1 over T2 minus 1 over T1. So we are going to insert all the values that we have here given in the question inside this Arrhenius equation. So it's going to be ln 0.134, this is K1, liter per mole per second, over 0.569 liter per mole per second. Okay, we have to solve this first before we press ln, and then we want to find EA. The R is the energy constant, which is 8.314. If you don't remember that, you can go to the back of your book at page 389. You can see that there is an appendix A there. The unit for this constant is joule per Kelvin per mole. Okay, and then we have to insert the values of temperature. The temperature of T2 is 1 over 450 minus 1 over 300. Okay, right. So you're going to do a bit of calculation using your calculator, and the final answer would be 108 to 1.23 joule per mole, and then we convert it into kilojoule because activation energy has the unit of kilojoule per mole, so it is 10.8 to 1 kilojoule per mole. This is the final answer. Your task is to do practice 3.4 where the rate constant K1 and K2 is given 3.7 times 10 to the power negative 5 and 1.7 times 10 to the power negative 3 per second. This is first order. It's just that in your course book, page 97, the temperature for K1 given is 25. So change it into 5 degrees Celsius. And for K2 also, in your book is 5, change it into 25. We want the activation energy to become a positive value. That's why we need to change the delta T here. This is question number 2. You need to find the value of T. So you can give it in Kelvin or degrees Celsius. The last factor that will affect the rate of reaction is the particle size. The smaller the size of reacting particle, the greater is the total surface area exposed for reaction, and the faster the reaction will be. In the case of heterogeneous systems in which the reactants are in different phases, the area of contact between the reacting substances will influence the reaction rate considerably. Here in figure 3.22, you can see the greater the surface area of a solid, the higher the reaction rate. A greater area causes a greater frequency of collisions, thus increasing the reaction rate. That's all for chapter 3, reaction kinetics. Thank you very much for watching and paying attention to all the lectures, starting from the rate law, differential rate equation, integrated rate law, and the calculations, collision theory, and now the final one, the factors affecting the reaction rate. Assalamualaikum warahmatullahi wabarakatuh, students. I will see you in organic chemistry. Bye.